SUVAT equations. So SUVAT actually stands for the following. S in physics stands for displacement. U, initial velocity. V, final velocity. A is acceleration. And T is time. So when you hear SUVAT, that's what it means. It really stands for those things. And these are quantities that are used throughout Year 11 and Year 12 physics. Okay, these are things that we experience every day. Displacement, for example, is a measure of how far you are from your starting point. Okay, it's a vector, so it's got direction. Suppose this is my house. I start at my house and I go east to school, and then the distance is, let's say, 20 k's. My displacement when I'm at school, when I'm standing at school, is 20 k's east, okay, from my house. Initial velocity, that's your starting velocity. That's your starting speed in a particular direction. Let's suppose I'm driving a car. This is a bird's eye view looking from above. Initially, I'm at standstill. So my initial velocity, we give it the symbol U, is 0 k's per hour, for example. Then final velocity, let's suppose I want to measure my velocity at a certain point. Let's call it X along the road. Final velocity will be measured to be V, and that's, let's say, 50 k's per hour. Acceleration, that is the rate of change of velocity over time, okay? How fast your speed is changing, in other words. Okay, and acceleration is given mathematically by the following. So lowercase a for acceleration is the rate of change. So we use the Greek letter delta. It's a capital delta. It means change velocity over change in time, t. And time, we give it the symbol t. Time ticks away at a rate of 1 second per second. Okay. Let's explore the SUVAT equations. Now, I'm going to derive them for you. You will most likely not be expected to derive these in an exam. I personally wouldn't ask it. It's not really fruitful, but anyway. I'm going to start with acceleration. So acceleration A is the rate of change of velocity over time. The more you press down, so I want you to picture this, the more you press down on your accelerator pedal in a car, the more you're going to accelerate, okay? The more rapidly your speed's going to change. If I was to graph, let's say, displacement over time, so let's say how far I am from my starting point when I leave my house, let's say, in my car, and I accelerate, it's going to look like that. It's going to be rapidly increasing, almost exponentially. Okay, it's not really an exponential, but anyway, it means I'm covering a lot of ground here in less and less time. Okay, that's acceleration. I'm going to begin with this. So the delta really means final minus initial, always, okay? Final minus initial. It's just, we're lazy people, physicists. We like to write things in shorthand notation. So instead of writing always final minus initial, we just use delta. It's a triangle with a slightly bold right side. That in turn is equal to V minus U. Remember, V is final velocity from above here. U is initial velocity all over time. Now, I'm going to do this. I'm going to keep it as T. Okay, let's suppose that the initial time is 0. Okay, and we've got the final time. I'm going to leave out the F, okay, for final. T sub F. I'm just going to write it as T, okay? Now this, we can rearrange this as follows. All I've really done is, using a bit of algebra, it's taken the T, multiplied it by the A, and that equals V minus U. And we can write an expression for the final velocity V as follows. V equals U plus AT. If I take this guy over, remember the rule is the minus becomes plus. And that is our first SUVAT expression there. Your final velocity is given by the initial velocity plus the acceleration times time. That's equation 1. Use a different color. Okay, second expression. Let's begin with this. Now, we know that displacement, or we know for speed, I should say, speed, V, is distance over time. Okay, speed is how much ground you cover in a certain amount of time. That's speed. Okay, we give it the symbol V. Now displacement, so v, okay, velocity, okay, speed is velocity is speed with an arrow on top with a direction. That's why I put a vector there, an arrow. It's displacement s over time. Okay, and I should say here average velocity. Okay, average velocity, because if you start at one point and you finish at another point, you need average velocity, and you want to calculate velocity. That's your average velocity there. Okay, because it involves your entire journey, and your velocity may change over the entire journey. That's why we use average velocity. So based on this expression here, displacement is just simply ignoring the arrow for now, the vector, average velocity times time. But when you average something, let's say I've got initial velocity here, final velocity here at my destination. Average simply means you take the two velocities here, add them up and divide by 2. So you get u plus v over 2. Okay, that's average. If I was to tell you find the average of 2 and 3, you would do 2 plus 3 and divide it by 2, how many numbers there are, okay? And the t stays where it is. Now let's plug in, because we can, v from before. V is simply, it's getting messy. Use a different color. V here, v is just u plus at from before, right there. So let's plug in for v u plus at, so that equals, I'll go back to purple. So u plus, I'm going to plug in my v now, u plus at, all of that divided by 2, parentheses there, t. Let's tidy up this rubbish. Now, collect terms, u plus u is 2u. Okay, and the at stays, all over 2t. That's what we're left with. Doing some cancellations and expanding the brackets. So in this case here, the 2's cancel out, so left with u, but if you multiply it by the t there, you get ut plus, because it's at over 2, that's just half at. I should say a t squared, yeah? Okay, because at over 2, that's the same thing as saying a half at, and then at times t is at squared, yeah? And that right there is your second expression, second SUVAT expression there. That's how you calculate displacement in terms of initial velocity, acceleration, and time. Okay, let's get on to the third expression now. Okay, let's start with v equals u plus at. Let's square both sides, because we can. Okay, whatever you do in maths to one side of an equation, you must do to the other side, okay? It's v squared equals, now this has to be all squared, okay, because it's one expression. Square that. Expanding the square, that's u squared plus 2uat plus a squared t squared. Okay, let's assume knowledge there, knowing how to expand a square. If we tie this up a bit, collect like terms, we'll take out the 2a here. So we get ut left over plus half at squared. Now, why did I do this? Well, if you look at this, I'm sure it might be ringing bells already. This thing looks familiar. That is just this. That's just s. So we have now our third SUVAT equation, u squared plus 2as. Okay, and that's v squared. That's how you can work out final velocity in terms of initial velocity, displacement, and acceleration. And they're your three SUVAT equations there. First one's v equals u plus at. Second one is s equals ut plus a half at squared. And the third is v squared is equal to u squared plus 2as.